Good day, viewers. We are welcome once again to the continuation of our series on the physics lesson. And today we are going to be starting with sound wave. We are going to try to look at all the important areas of sound. Sound is a form of energy that causes the sensation of hearing. When we're defining light, we said light is a form of energy that causes the sensation of sight. When light comes to your eye will understand what is sending the light. So the same thing for sound. When sound comes to your ear, you have an idea of what is being said. So sound is also a form of energy, just as it's also an example of waves. So sound is a form of energy that causes the sensation of hearing. And we can classify it. One, apart from the fact that it's a form of energy, it's also an example of waves. For example, we can say that sound, we know when we're treating waves, that sound is a mechanical wave. It requires a material medium for its propagation. It means sound cannot travel through vacuum. Before you can have sound, you must have a material medium that is propagating, through which the sound is being propagated. We also understand that sound is a longitudinal wave. In fact, it's a principal example of longitudinal wave. So sound looks like a wave, an example of a wave that is on the opposite side of light. While light is electromagnetic, sound is mechanical, and while light is transverse, sound is longitudinal. Sound, being longitudinal, propagates itself as a series of refractions and compression. Anytime you make sure that sound goes, anytime sound has to propagate itself through air, it will go through air with its in form of compressions and refractions. As a wave, we expect sound to have a velocity. We also expect sound to have frequency, and we expect sound to have wavelength. Velocity of sound is the speed with which sound moves through a material. The speed with which sound moves through a material, and the velocity of sound is usually affected by, number one, the medium through which the sound is traveling. The sound travels through a solid medium. It is fastest when it travels through liquid. It is faster, and it is fast when it travels through gases. What I'm trying to say is the velocity of sound is fastest in solid, they're moderately fast in liquids, and is just fast in gases. Sound travels fastest in solid. So the medium through which sound is traveling determines, can or affect its velocity. Another thing that affects the velocity of sound is the temperature of the medium through which it is traveling. The temperature of the medium through which the sound is traveling. It is known that the speed of sound is directly proportional to the square root of the absolute temperature. When I say the absolute temperature, I'm talking about the temperature that is in Kelvin. The temperature that is in Kelvin is the absolute temperature. So I can turn this to an equation that should have V1 is equal to K square root of theta. Okay, V is equal to K square root of theta. It means the constant must be equal to V all over root theta. If the constant is V over root theta, I can say V1 all over root theta 1 must be equal to V2 all over root theta 2. The formula is important for me to find the velocity of sound at any temperature if I know the velocity of sound at a particular temperature. The third thing that can affect the velocity of sound is the wind velocity, particularly the velocity of sound in air. The wind direction and the wind velocity can affect the velocity of sound. When sound is traveling in a direction that is the same with that of the wind, it will be wind assisted, and we expect the velocity of sound to increase. When sound is traveling against the direction of the wind, we expect the velocity to drop. So the velocity of sound is affected by the medium, the temperature of the medium, and the wind direction. Frequency of sound. Sound being a wave has frequency. Humans do not respond to sounds of all frequency. Humans do not respond to sound of all frequency. In fact, there are so many sounds going on around us that we cannot hear. And most of the time, it is due to the frequency. I'm not even talking about the loudness. There are frequency of sound that we cannot respond to, we cannot hear. Sound that is within the audible range of man is between 20 to 20,000 hertz. So therefore, man cannot hear sound that is less, whose frequency is less than 20. A man can also not hear sound whose frequency is above 20,000. Sound of frequencies less than 20 will be called infrasonic sound, while sound of frequency above 20,000 will be called ultrasonic sound. We cannot hear infrasonic sound, we cannot hear ultrasonic sound because their frequency is beyond the range of audibility of man, which is just between 20,000 to 20,000 hertz. Any sound whose frequency is outside this range, we cannot hear. It is not possible for us to hear it, though it can have some scientific uses. For example, ultrasonic sound can be used for scanning in medical laboratories. So that is all about that. Sound being a wave also can undergo almost all of the properties of other waves. Sound can be reflected, can undergo reflection. Sound can be refracted, it can undergo refraction. Sound can be diffracted. Sound can be diffracted. Sound can undergo interference. The only other thing now is polarization, and sound, not being a transverse wave, cannot undergo polarization. So when we talk about the reflection of sound, we're talking about sound hitting a particular surface and being reflected back to the incident medium. All waves can be reflected. Light can be reflected. We have dealt extensively with that. Sound too can be reflected. In fact, the sound that is heard after the reflection of sound is called echo. Echo is the sound heard after the reflection of sound by a hard and rigid surface. Usually sound is reflected by a hard and rigid surface. We said light is reflected by a very smooth surface. But if the surface is hard and rigid, particularly like a wall, it can reflect sound. And any sound that we hear after the reflection of sound can be called echo. So when the echo becomes multiple, sound that comes from multiple reflection of sound is called the reverberation. And usually reverberation constitute nuisance, particularly in auditorium where lectures are being delivered. So because of that, we generally need to pad the walls with material that can absorb instead of reflect sound. Soft material, soft bodies absorb sound. So when you enter into a very big hall and see that the walls are padded with very soft materials or soft materials generally, it is for the purpose of absorbing the sound instead of reflecting it, such that it will not generate multiple reflection of sound whenever the speaker is delivering his or her speech. In such cases, we can minimize reverberation. Now, there are so many uses of echo. I said echo is the sound heard after the reflection of sound by a hard and rigid surface. One of such is the determination of the speed of sound. We are able to know the speed of sound principally because we can employ echo for the purpose. There's another thing that is called echo sounding. Echo sounding also has another name. It is called echolocation. And there's the detection of submarine in war zones, detection of submarines. Detection of submarines can be used for the detection of submarines. And sound can also be used for the exploration of mineral resources, exploration of mineral resources in different regions of the world. We are going to try to talk about the two most important aspects for this course. That is the determination of the speed of sound. If a man faces a wall, of course, if the man makes some sound, we expect the echo to return. Let us assume that the distance between the man and the wall is d. If a man makes a sound and the sound is reflected back to the man, the time it takes the sound to come back to the man, let us call it T. If we can measure the distance between the man and the wall, that distance is D. So we expect the echo or the sound to have traveled a distance that is equal to 2D. 2D because it will have to move from the man to the wall and it will come back from the wall straight to the man. So it has traveled a distance of 2D in a time that has been recorded as T. I can therefore find the velocity or the speed with which the sound travels as the distance all over the time. The distance taken by the sound is 2D and the time spent by the sound to cover that distance is T. So with that, I can easily find the speed of sound. But one precaution that I must take in doing this experiment is I must ensure that the distance between the man and the wall is large enough. If the distance is too small, the echo will not be observable. That is why most of the time when you are sitting in your own room of very small length and breadth, you hardly hear echo. It is not because echo is not formed, but the distance between you and the wall is so short that the echo is returning back in a time while you are still hearing the original sound. I will go over that again. The natural human response time is known to be about 0.1 seconds. That means whatever sound that we want to hear, it takes us a short period of time to hear it. We don't hear it just within an instant. It takes us some moments to hear. The time that it takes us to hear the sound is 0.1 seconds. If your echo returns back to you while you are still hearing the original sound, you will hear it as part of the original sound and you will not be able to distinguish it as echo. Meaning that before you can hear a distinguishable echo, the echo must return after you have heard the original sound. If I utter the word A, that's the original sound. I expect the echo to come back after I have heard the original A. But if the distance between me and the wall is so short, such that the reflection process of that sound returns the A, the echo of that A back to me while I am still hearing the original sound within this period, then I will not hear it as a distinguishable echo, and I would think that echo has not been produced. Echo is always produced. It is just that we need a sufficient distance between us and the reflecting surface before we can hear a distinguishable echo. Now, like we said, sound can also be used for what we call echo sounding. Another word for echo sounding is echolocation. The meaning of echolocation is the process of determining the depth of a sea with the help of sound. The process of determining the depth of a sea with the help of sound. If you have ship traveling on the sea, most ships have what is called the transmitter and the receiver. The transmitter sending sound. The sound is reflected at the seabed and it returns back to the ship. The echo that returns back from the reflection of that sound is picked up by the receiver. If, for example, it took a time T for the sound to go through its downward and upward motion, let us say T, and we know the velocity of sound in water, I can find the depth of the sea, presently represented as D, which is the distance between the ship, the surface of the water, and the seabed. Remember that the velocity is equal to the distance all over time. The distance must be equal to velocity multiplied by the distance. Speed must be the distance all over time. That means the distance must be velocity multiplied by time. The distance in this case traveled by the sound is D plus D, which is 2D, where D represents the depth of the sea multiplied by velocity times time. My D therefore must be velocity times time divided by 2. And that should give me the formula that I will use to find the depth of the sea. When I do that, I'll be engaging in a process that is called echolocation. Echo can also be used to detect submarines in war zones. and can also be used to explore for mineral resources in certain regions of the world. Now, echo sound can undergo the other processes too. Sound can be refracted, and sound can be diffracted. It can also undergo the process of interference because it is a wave. Refraction of sound is what is responsible for why it is possible for us to hear sound coming from a great distance at night than during the day. During the night, we expect that the air layer that is closer to the ground, is colder, while the air layer that is above is hotter. If that is the case, it means when sound is released from a far distance, we know that sound travels faster in hotter medium because the velocity of sound is directly proportional to the square root of temperature. When the sound is released in hotter regions, what that means is it tries to travel and tend to travel in colder region where it will move slower. Because it travels slower in colder regions. Even humans, if you have a place where you will be made to run at all times and you have a place where you'll be made to just walk, our natural body shift will be to walk in the direction, to go in the direction that we always want to make us walk, because we believe under that condition we exert less amount of energy. So when sound is released in hotter region where it moves very fast, we expect that its path will be curved downward as the temperature reduces. And that way, once sound is brought to the ground, it is possible for us to hear it. During the day, we have an inversion of that. Colder air is up, while hotter air is down. If sound is now released at any distant point, if it travels in colder region, it will continue to always want to travel in even colder regions, so its direction will be refracted away from the ground. The change in the direction of sound, because it is moving between media of different densities, is what is called refraction, and it is responsible for why we hear sound coming from a far distance during the night than in the day. Diffraction, sound can also bend its path around an obstacle. Sound can bend its path around an obstacle. That is the exact meaning of diffraction. That is why it's possible for you to stay in a room, lock your door and window, and when you speak from the room, if you have anybody outside, it's still possible for them to hear you, because sound will find a way to travel through the holes around the doors and the windows. So sound can actually bend its path around an obstacle because it can be diffracted. Interference is the superposition of waves that are traveling in same direction, waves that are traveling in same direction, having the same frequency, amplitude, and probably wavelength. If waves have the same frequency, amplitude, and wavelength, and they are moving in the same direction, they can undergo interference. So sound can also undergo interference because it is a wave. If it undergoes interference such that the wave joins together at like points, then it's going to give us a larger wave, and that was what we discussed as constructive interference under waves. Sound can interfere constructively, it can join constructively. When it does that, we are going to hear a louder sound, though it is also possible for sound to interfere destructively. But sometimes we have effects that are not really interference, but they are so close to it. When we bring sound of close frequencies together, sound of close frequency, let's say F1 and F2, that are so near, what is required for interference is that the two waves must have the same frequency. Where they do not have the same frequency, such that their frequencies are only very close, when you compare them, when you bring them together, they start to give you what we call beats. There are times, I said when sound interfere, when they interfere constructively, they give you a louder sound. It means when they interfere destructively, they give you a silent sound. When you now have the combination of two sounds, and there are points where the sound has a very has an increased loudness, and there are points where the loudness is almost zero, and that continues periodically. We will say what you have is not really interference. What you have is called beats, and beats is an effect that you can only produce when you merge sound of close frequencies together. Beat is the periodic variation in sound when the periodic variation in the loudness of sound when two sound notes of close frequencies are played simultaneously. Beat is the periodic variation in sound which is heard, the periodic variation in the loudness of sound, which is heard when two sound notes of close frequencies are played simultaneously. We can now be asked to find the beat frequency. Is one of the simplest things that you can ever find in physics. The beat frequency is just the difference between the two frequencies of the sound that you are playing together. Note that the two of them do not have the same frequency, they only have close frequency. Let us assume that one has a frequency of 50, while the other has a frequency of 51. Yes, 50 and 51 are close. When you bring them together, they will form beats. And when they form beats, the beat frequency can be calculated as 51 minus 50, which is 1 hertz. That is all about the property of sound. We move on to the characteristics of a sound note. The characteristics of sound notes. I want to call the sound notes as the simplest sound that you can use to study sound itself, the simplest form of sound that you can alter, something that looks very much like a syllable in English. If I alter the word A, that is a sound note. That sound note has 3 characteristics. Number 1, it has what is called a pitch. Number 2, it has what is called loudness and intensity. Then it has what is called quality. Those are the 3 properties of a sound note. And these properties allow you to differentiate the note that comes from a person as different from the note that comes from another person. The pitch of sound is the position of that sound on a musical scale. Any sound that we alter has a position on a musical scale. The position on the musical scale is the pitch of the sound. Something that sounds like the sound that you give to your words, like do, re, mi, fa, sol, la, ti. All of those are the pitch, which represents the position of any sound that you alter on a musical scale. It is more commonly used in the world of music, but what we just need you to understand here is that the pitch of a sound note is a function of the frequency of that sound. In fact, in some textbook, they will outrightly define pitch as the frequency of sound. It is not the frequency exactly. It's a measure of the frequency of the sound, but it is more appropriately referred to as the position of that particular sound on a musical scale. Now we'll move on to other characteristics of sound notes. That is loudness. Loudness is something that we directly understand. Loudness is the amount of sensation resulting from the speaker, the amount of sensation that is getting to the listener. If I alter the word A and I alter the word A, we all understand that the second sound is louder. It is coming with an higher energy. It is coming with a greater power. So when you release sound with a great amount of energy, it definitely must have very good, it must be loud. The loudness of sound is directly related to 3 different properties. Number 1, it is related to what we call intensity. Number 2, it is related to what is called the amplitude. And number 3, it is related to what we call the amount of air that you can set into vibration. Amount of air set into vibration. Intensity, of course, if you speak with a great intensity, the sound you are going to alter will be louder. If you speak with just small amount of intensity, then the sound that you are going to alter will be silent. Intensity is a measure of the amount of energy that you put into your speech. Therefore, intensity is defined as the rate of flow of sound energy per unit time, per unit area perpendicular to the direction of sound. If I want to get the intensity, anytime you speak, you will understand that you are giving out power. You can actually put your palm in front of the direction of your sound, the sound that is coming from your mouth. When you do that, you start to feel the energy with which the sound is coming out of your mouth. When you are altering very silent sound, you will discover that the amount of energy that you are going to be feeling on your palm is low. When you are altering sound that is coming with great power, great energy, then you will understand, you will feel it on your palm, and you will discover that it will be louder to whoever is listening. So the intensity of sound is a quantity that allows us to put your power to put your power into a context that we can now measure it. We said the intensity of sound is the rate of flow of sound energy per unit time, per unit area that is perpendicular to the direction of sound. So I will define intensity. If I want to find it, it will be the sound energy all over the time, the rate of flow of energy per unit area. This will outrightly become the formula for finding the intensity. I expect you to know that the unit of energy is joules, the unit of time is seconds, while the unit of area is meters squared. If you do all of that, you have the unit as joules per seconds per meter squared. And if you already know that joules per seconds is watt, so this can also be put in watts per meter squared. The amplitude is a parameter that comes with the wave pattern that I want to use to represent my sound. I was telling you while we're doing wave that you can refer to our class on wave for that. Waves can be represented graphically with sinusoidal curves. The amplitude is the maximum displacement from the rest position. In a situation where a sound wave can be represented like this and another can be represented like this, then we clearly know that this other one will have an amplitude that is greater than the first. So the loudness is always directly proportional to the square of the amplitude. Another thing that can affect loudness is the amount of air that you set into vibration. Sound results from vibration. That's the very first thing we must establish. Sound results from vibration. Any vibrating object must produce sound. Or if an object is to produce sound, there must be something within it that is going to vibrate. Anytime you set an object into vibration, it must produce sound. So if an object is set into vibration, it will pass its vibration into the air. It is the air that will now propagate it as sound. The amount of air that you can set into vibration, the amount of contact between the vibrating object and air will also assist the loudness. Where you can set large amount of air into vibration, then it is possible for you to generate a very loud sound. That is why if I take this marker and I start to tap it, yes, you will hear the sound, but not so loud. If I now decide to tap it against the board, it becomes louder. Why is that so? As I set this marker into vibration, it is only the air around it that will vibrate with it. But when I press it against the board and I vibrate it against the board, it will pass its vibration to the board. So the board too will start to vibrate. And look at the surface area of the board. It is in a position where it can set large amount of air into vibration, and whatever sound that comes from its vibration will be louder. So the loudness depends on intensity, it depends on the square of the amplitude, and it depends on the amount of air that we can set into vibration. The last property of a sound note is quality. Quality of a sound note is a property of the note which distinguishes it from another note of equal pitch and loudness but played by another instrument. I'll go over that again. Quality of a sound note is the property or the characteristics of a note which distinguishes that note from another note of same pitch and loudness with it, but played by another instrument. As if I decide to alter the word A, it is possible for you to mimic that A that I've said exactly in pitch and loudness, but you can never mimic it in quality. No matter how hard, how good we try to play out the same sound, those sounds will have different quality if they are either played by different instruments or said by different people. Quality is a property of that particular instrument that is altering that sound or that is playing that sound. So quality depends on the nature of that instrument. And because of that, except you can manufacture an instrument that is exactly alike with it, it is definitely impossible for you to produce two sound notes of the same quality by different instruments. So when two sound notes are played by two different instruments, even if they have the same pitch and they have the same loudness, they can never have the same quality. Quality is a function of the instruments that you are using to play out the sound. We usually say that the quality of sound is a function of the overtones and harmonics. What are overtones and harmonics? I want us to keep our fingers crossed as we continue to review the gray area under this topic. We move on. There are other terms that we should now just try to define. What are those terms that we should talk about? Noise and music. Oftentimes we tend to hear this word noise and we tend to hear music. In physics, the two of them are just defined with reference to their frequency. Noise is sound produced as a result of irregular frequency. Noise is sound of irregular frequency. When you have people talking at different frequencies and the sound they are producing is jumbled up, then you are going to have what is called noise. That looks very much like what we call noise even in our day-to-day life. Music, however, is a sound produced from regular frequencies. The sound produced from regular frequency. When the frequencies are regular or when the frequency is constant, then we have what is called music. Another concept that we should talk about is force vibration and resonance. I'll start this by saying that sound result, we established it earlier, that sound results from vibration. Anytime you have to produce sound, something must vibrate. If you are going to beat a drum, the membrane of that drum must vibrate. If you are playing a flute, there's air inside the flute that you are setting into vibration. If you are playing out a guitar, there is the string on that guitar that is going to start to vibrate. We are still going to see all of this when we get to types of musical instruments. Even human, there's a vocal cord in us that is vibrating as we are speaking, and that is what is making us to be heard. Without it, we can talk, but nobody will hear us. We can talk, but nobody will hear us. Now, sound results from vibration. Another thing I must add to that before we now get to what we need to explain force vibration and resonance is any object when set into vibration will vibrate at a particular frequency. If I set this board into vibration and it starts to vibrate on its own, it will vibrate at a frequency that is called its natural frequency. Any object when set into vibration, when allowed to vibrate freely on their own, there's a frequency with which they will vibrate. That frequency is called the natural frequency of vibration of that object. Natural frequency of vibration of that object. Let me use this board as an example. If I hit the board and I allow the board to vibrate, of course the vibration will die down due to what is called damping. We are going to see that later in simple harmonic motion. But let us assume that its vibration can be continuous. If I set it into vibration and I leave it, it will vibrate at its own natural frequency. Now, let us assume that the natural frequency of the board is 5 Hertz. Natural frequency of the board is 5 Hertz. If I set it into vibration and I do so continuously because I don't want the vibration to go off, I keep vibrating it. Now, I have two different systems. I am forcing it to vibrate. So the board becomes the forced system. My hand will be regarded to as the forcing system. I can also be called the driving system, while the board will be called the driven system. When a forcing system acts on a force system, the force system will have to vibrate at the natural frequency of the forcing system. If, for example, the natural frequency of this board is 5 Hertz, and I am hitting it at my own frequency of, let's say, 1 Hertz, the rate at which I'm hitting it is 1 Hertz, it will start to vibrate with 1 and not with its own 5. Bodies vibrate when bodies are under force vibration. When they are experiencing force vibration, they will vibrate with the frequency of the forcing system, not with their own natural frequency. So if I hit it with 1, it will vibrate with 1. If I hit it with 2, it will vibrate with 2. If I hit it with 3, it will vibrate with 3. If I hit it with 4, it will vibrate with 4. When that takes place, I will say that the board is undergoing a force vibration. So I will define force vibration as those vibrations that result from an external periodic force acting on a system and setting the system vibrating as with a frequency that is equal to the frequency of the external periodic force. Force vibration are those vibrations that result from an external periodic force, my hand, acting on a system, the board, and setting the board vibrating at frequencies which are equal to the frequencies of the external periodic force, frequency of my hand. I'm setting it into vibration and it's having frequency with not its own frequency, not its own natural frequency, but my own frequency. Why resonance occur when an external periodic force, when an object is set into vibration at its own natural frequency, is set into vibration at its own natural frequency as a result of impulses that it is receiving from external periodic force, which are vibrating at that same frequency. I will explain. I said if the frequency of the board is 5 and I start to hit it at 1, then it will start to vibrate at 1, which is not its own natural frequency. That becomes forced vibration. I'm making it vibrate in a way that it does not want to vibrate. It wants to vibrate at 5 naturally. So forced vibrations are vibrations that result from an external periodic force acting on a system and setting the system into vibrations at frequencies which are equal to those of the external periodic force. Now, when does it now become resonance? It becomes resonance when resonance is also a special example of force vibration. Now, the natural frequency of this object is 5, and I decide to start to hit it at 5. Yes, it's going to start to obey me, but coincidentally, it's going to obey me in a way that it also wants to move. It will start to vibrate at that 5. If it's vibrating at 5, then I will say there is resonance. So resonance occurs whenever an object is set into vibration at its own natural frequency as a result of impulses that it is receiving from an external periodic force that is vibrating at those frequencies too. When an object resonates, when an object undergoes resonance, that is when it vibrates with the largest amplitude. That is when it vibrates very well. That is when it produces the loudest sound, because amplitude under sound is represented with loudness. When you say, I said it earlier, that when the higher the amplitude of sound, the louder it becomes. So if you want a system to resonate, if you want a system to undergo maximum loudness, then you must allow it to resonate. You must set it to vibration, and you must allow it to vibrate at its own natural frequency. There's even a graph that is common to see in most textbooks where the amplitude that you get anytime you set an object into vibration is plotted against the frequency of vibration. For this example, for this one, if I if I set it into series of frequency values, if I hit it with series of frequency values, let me say from 1 to 10, when the frequency that I'm using to hit it is 1, it will have a particular amplitude. When it's 2, the amplitude increases. 3, it increases. 4, it increases. At 5, because 5 is its natural frequency, it will have the highest amplitude. And at 6, the amplitude will start to drop. 7, it will drop. 8, it will drop further. 9, it will drop further. And it will. So if we join those points, we'll have a dumbbell. We will have a dumbbell shape, and this is the graph that you get anytime you plot the amplitude of vibration of a system against the frequency of the external periodic force that is attempting to set it into vibration. And that is all. There can be so many examples of a resonating object or an object that is also set into force vibration. If a man is playing a guitar, your hand becomes the driving force, while the guitar is the driving system. When you are beating a drum, your hand becomes the driving force or the external periodic force, while the membrane of the drum while the skin of the drum is the driving system. Now we are going to move on to examples of vibrating system, and we are going to try to see how vibrations in strings look like. Vibrations in strings. When we are done with vibration in string, we'll look at vibrations in pipe. And from vibrations in pipe, we'll look at resonance tube. And with that, we should draw the curtain on the topic vibrations in string. Why are we studying vibration in string? Why do we even need to know how string vibrates? Because string makes up a third of the musical instrument that we have. There are 3 musical instruments. We have stringed musical instruments, those that have vibrating strings in them. We have percussion musical instruments, those that have an elastic skin that has an object that can either be beaten, stuck, or set into vibration by an external force. And we also have what is called wind instruments. Those are examples of things that you have to blow with your mouth. A flute is a very good example of such class of musical instruments. Vibrations in strings. When you take the string on a guitar, for example, those strings have length. They have masses, the mass of the string, and they come in different type. Very thin string are very light because they do not contain much of the string material. They can also have very thick string. Those ones have higher masses. So when they line up the string on a guitar for you, the next time you see it, you can try to observe the thickness of each of those strings. You'll see that they are actually different. The reason why they are different is because they are made to have different masses. And there's something we are going to get from the mass of the string very soon. They have string, they have masses. Then we can find what we call the mass per unit length of the string. We can find the mass per unit length. The mass can be in kilogram, while the length is in meters. So we expect the mass per unit length to be in kilogram per meters. Now there are knots that you can use to tighten the string also. When you tighten a string, you are increasing the force along it. The force along a string is called the tension. The force along a string is called tension, and I'm going to represent it by T. The force along a string is called the tension. With the tension and the mass per unit length, I can find the velocity of sound that will be produced by that string. The velocity of sound that will be produced by a string is the square root of the tension divided by the mass per unit length. If you know the tension along a string and you know the mass per unit length of that string, you can divide them, then you will have the tension. You will have the velocity of sound along that string. We can continue. Now that I know the velocity, let us try to talk about the wavelength, because there are just three parameters for a wave: the velocity, the frequency, and the wavelength. If I can get the velocity, I can get the frequency, then I should be able to know how to get the wavelength. To study the wavelength of vibration of a string, let us write the formula for the velocity somewhere. The formula for the velocity is T all over m square root. Now, if I have a string, let us also assume that we have another string. Let's say we have another string. The velocity depends on the pattern of the wave with which it is going to vibrate. Note that when we're talking about wave, I said if you generate a wave on a string, when the wave gets to the other end, it will most likely be reflected. If it is reflected, we have what is called the incident plus the reflected wave should give us what is called a stationary wave. It was part of the waves that we defined in our class on waves. You can refer to the video that we have made on that for you to properly understand what we are talking about. Now, I was also saying that there are two important points on a stationary wave. Point of maximum amplitude, that is the antinode, and point of zero amplitude, that is the node. Point of maximum displacement, that is the antinode, then we have the node. The antinode, then we have the node. I must be able to express the antinode and the node in terms of wavelength. I must be able to express the antinode and the node in terms of wavelength. If I have a wave, yet I defined the pattern that forms a wavelength, I define it to you. I said a crest to a crest is a wavelength. A crest to the next crest is also a wavelength. A trough to the next trough is a wavelength. Now, this is when the wave is still just progressive. If I join this wave to its reflection, such that I now have this was a crest, this was a crest, this was a crest, such that I now have a stationary wave. Then all of this crest becomes, let me even study two crests. This crest becomes an antinode, and this crest also becomes an antinode. And due to the fact that I am now mixing it with another wave, an antinode has been formed between the two. It clearly means that because I have an antinode between the two, the definition of wavelength is still the same. Because this was where we had the crest before, this was where we had the crest before. Now it has changed to an antinode, now that we have changed the wave to a stationary wave. Now, if this to this is still a wavelength, I can therefore say that the distance between an antinode and the next antinode is half of the distance between a crest and the next crest. So an antinode to an antinode must be half of a wavelength. I'll go over that again. If you have a transverse wave, points of maximum upward displacement are called crests. Points of maximum downward displacement are called trough. If we turn this wave into a stationary wave, I was saying that generally I define it. Please check our class on wave for you to understand the different ways by which we can define a wavelength. A wavelength is the distance between successive troughs, and it's the distance between successive crests. That was when we had the progressive wave. Now that we have joined the reflected wave to it, we'll see that all of the crests becomes antinode and antinode, and there's a new antinode that has even been created between it. I said if the distance from a crest, what used to be crest, to the other point that also we refer to as crest is a wavelength, still a wavelength. The fact that the form has changed from traveling wave to a stationary wave does not mean that the wavelength will now change or become smaller or larger. No, this is still a wavelength. Only that now we now have an antinode between the two antinodes that were formed from the crest. So now the distance from an antinode, I wish to express it as the distance to the next antinode. If from here to here is a wavelength, I expect the distance between successive antinode to also be half of a wavelength, because it is half of the distance represented by the wavelength. So the distance from an antinode to an antinode, don't forget, is half of a wavelength. Now, if the distance from an antinode to an antinode is half of a wavelength, note that a node is between an antinode and the next antinode. So I can also be asked to find the distance from an antinode to the next node. That should be a quarter of a wavelength. From an antinode to a node is a quarter of a wavelength. So antinode to node must be a quarter of a wavelength. From the node to the next antinode should also be the quarter of a wavelength. So that is why antinode to an antinode is half of a wavelength. From antinode to the next node, node is here, antinode is here. From antinode to the next node is also a quarter of a wavelength. So I can now be asked that what is the distance from a node to the next node? From a node to antinode, a quarter. From an antinode to a node is also a quarter. So node to node must be quarter plus quarter, and that is also half of a wavelength. So any pattern that gives us a node to a node is half of a wavelength, antinode to an antinode is half of a wavelength, and antinode to a node is a quarter of a wavelength. If you are given any pattern, most times you might just have to be required to find the number of wavelengths that it has. And one easy way to do that is to count how many of these combinations you have in the pattern that is given to you. Now we want to check how a string can be set into vibration. A string can be set into vibration in so many modes, but the simplest mode of vibration of a string will be obtained if you just press the midpoint down. If you press the midpoint down, a wave of this form will be obtained. It will sag downward. When it gets to the other end, we expect it to be reflected. This is a wave. When it gets to the other end, it will be reflected, so we have a stationary wave. Another form of vibration of a wave is to hold the midpoint down and play out the middle of one segment of the rope. If you hold the midpoint down and you play down the middle of the segment of one segment of the rope, we'll have that segment sagging downward. When it gets here, because there's still more rope, it continues. When it gets to this other end, it is fixed, so it tries to return in the reverse direction, and you have this. This is the next form of wave that is possible. Another one that is possible is if we hold it down at two different points and we'll play down one segment of the rope or play up one segment of the rope, we'll have this form. When it gets to the other end, I expect you to know that it will be reflected. That is why most times we see guitarists trying to hold down certain points along the rope on their guitar. It is to generate different pattern of vibration. Let us also assume that the length of the rope is L. If it is the same rope, I will say that the length of the rope here too is L. If it is the same rope, I will say that the length of the rope here too is L. So we can continue. If we decide to now express this in wavelength, let us express it in wavelength. This is a node, and this is another node. The number of wavelength that we get from node to node, I just showed you, is half of a wavelength. It means the length in this case must be half of a wavelength. This is a node, and this is the next node. This is another node. I expect you to know. Let us count the number of wavelength that this has. This is node to node, half. Another node to node is half. So half wavelength plus half wavelength gives us one wavelength. In terms of wavelength, it's just one. This is a node to node, one half. Another node to node making half. That is one. Another node to node, half again, making 1.5. Or better put, 3.5 lambda. So I am now going to express them, the length in terms of the wavelength that is giving me. This one wavelength is giving me L. Here, one wavelength is giving me 3/2L. 3/2 wavelength, sorry. The length here is giving me one wavelength. So let me make the wavelength the subject of the formula in each. The wavelength here, if I cross multiply the two, will be 2L. The wavelength here will be L, while the wavelength here will be 2L/3. Because this is the simplest mode of vibration, I'm going to call this wavelength the fundamental wavelength, and I'll represent it with lambda naught. The fundamental mode, this will be called the fundamental mode of vibration. This will be called, all other mode of vibrations that are possible after the fundamental are going to be called the overtone. This is the first overtone, the vibration of the first overtone. This is the vibration of the second overtone. So I'm going to call this the wavelength of the fundamental mode of vibration, or just simply fundamental wavelength. This is the wavelength of the first overtone. This is the wavelength of the second overtone. Now, if I know that, I can now use the wavelength with my velocity to find my frequency. Remember that V is equal to F lambda. If V is equal to F lambda, it simply means that F must be equal to V all over lambda. It means frequency must be equal to velocity over wavelength. So the frequency that I will get from the fundamental wavelength must also be the fundamental frequency, and that should be V all over the fundamental wavelength. That should be V all over the fundamental wavelength is 2L. I'll continue. The frequency I'll get from the first overtone must be the frequency of the first overtone, and that should be V all over the wavelength of the first overtone, and that should be the frequency of the first overtone is equal to V all over L. If I continue, the frequency of the second overtone must be V all over the wavelength of the second overtone. So frequency of the second overtone must be V all over 2L divided by 3. Frequency of the second overtone must be equal to 3V all over 2L. So if I have to do this, I have obtained the fundamental frequency in terms of V and L. I've obtained the first overtone in terms of V and L. I've obtained the second overtone in terms of V and L. So once you give me the velocity of the sound produced on a string, even if you don't give me, I can easily find it from this formula if I know the tension and the mass per unit length. And you give me the length. then I can find any frequency. But there must be a way by which I can express all other frequency in terms of the fundamental frequency. So that if I know the fundamental frequency and I know how to use it to get all other frequency, I can even continue to find more frequencies. Frequency of the third overtone, fourth overtone, fifth overtone, even frequency of the 10th, 20th, 40th overtone. Now, let me try to find the direct ratio of F1 to F2. If I divide F1 by F0, I should have F1 is V all over L, divided by F0 is V all over 2L. That should be V all over L multiplied by 2L over V. V cancel out V, L cancel out L, F1 all over F0 must be equal to 2. That means F1 must be equal to 2 F0. So my first overtone frequency is actually 2 times my fundamental frequency. If I do the same thing here, my F2 all over F0 must be equal to V all over 3V all over 2L divided by F0 is V all over 2L. If I do that, F2 all over F0 must be equal to 3V all over 2L multiplied by 2L all over V. This cancel out this, V cancel out V. F2 all over F0 must be equal to 3. That means F2 must be equal to 3 F0. So F2, the frequency of the second overtone, must be equal to 3 times the frequency of the fundamental frequency. So if I have F0 and the first overtone is 2 times F0, the second overtone is 3 times F0, I can say that the fourth overtone is 4 times F0. I can say that the third overtone will be 4 times F0. The fifth overtone will be 5 times F0. So the number that you are using to multiply F0 to get the particular frequency of the overtone, I can generalize it as the frequency of any overtone must be n plus 1 F0. And that equation applies. We can see clearly here that F1 is 2 F0. I've increased 1 by 2, and I'm using 2 to multiply. I've increased 1 by 1, and I'm getting 2 that I will use to multiply. If I increase 2 by 1, I'll get 3 F0. So if they want me to find the third overtone, it should be the 4 F0. The fourth overtone should be the fifth F0. The fifth overtone should be the sixth F0. And the sixth overtone should be the seventh F0, eighth F0, and so on and so forth. The number that you are using to multiply the frequency to get the overtone that you are looking for is called the harmonics. So listen to how I'm going to read them. The first overtone is the second harmonics. Second harmonics means the multiple of the fundamental frequency. So the second harmonics means 2 times F0. The second overtone is the third harmonics. The third overtone is the fourth harmonics. The fourth overtone is the fifth harmonics. So don't mix overtone with harmonics. If you want me to find the seventh overtone, that's F7. But if you want me to find the seventh harmonics, I'm talking about 7 F0. Harmonics has to do with the number you are using to multiply F0, while overtone is the position of the frequency that you are referring to. If you want me to find the seventh overtone based on that formula, it must be the 8th harmonics, and so on and so forth. We'll now continue with vibrations in pipes. Vibrations in pipes. There are 2 different types of pipe that we are going to be looking at. We are going to be looking at closed pipes or open pipe. Let us look at open pipes first, because that is more simpler and it looks very much like the string that we are coming from. Then we have closed pipe. Why is vibration in pipe important for us to study? Pipes form the element that is present in a third of musical instruments, flute, and those instruments that can be played, trumpets, those instruments that have vibrating air column inside them. It becomes open if we have a pipe that is open at both ends. If we have a pipe that is open at both ends, we refer to it as open. It becomes closed, however, if we have a pipe that is closed at one end. It can be closed at both ends. If it is closed at one end, then the pipe we refer to the pipe as closed pipe. Let me do one more for closed pipe. Open pipe have vibrating air column inside them. It is not like strings that vibrate in string instruments, but pipes have vibrating air column inside it. One of the structural difference between pipes and string is that we don't calculate the velocity of vibration of air. We don't. It's usually given to us as a constant. When you find the velocity of sound in air, it is given to us as a constant. But if you are to be string, I hope you know that we always calculate the velocity of sound produced by a string using the formula that I gave you earlier. The velocity is equal to square root of T all over the mass per unit length. Now, this end is free and this other end is also free. So what we will do, if we need to do this one, is to understand how free end vibrates with stationary wave. Free end vibrates with, when we're talking about string, we'll see that at every point, the string was giving us a node and another node at the ends. Why? Because the ends are fixed. If you have a free end, this part of the stationary wave that is commonly highlighted at the free end is an antinode. So if I'm going to have an antinode and an antinode, the simplest that I can have, remember that for spring 2, we started with the simplest. The simplest combination of an antinode and another antinode is what I've drawn. It is like having this. So when the ends are free, they will vibrate with maximum amplitude, and it is an antinode that you have there. The next antinode that we have, the next antinode to antinode combination that we will have will look like this. Antinode, I'll just add a loop to it. Another antinode. So this is an antinode at this free end, another antinode at this free end. The next possible mode of vibration that I will have is to add one more loop. I'll still have an antinode here and another antinode here. Mind you, just as the length of the string in the pipe will be given, the length of the air column will be given in the pipes. The length of the air column will be given in the pipe. I will name this, being the simplest, as the fundamental mode of vibration of air in an open pipe. I will name this the first overtone because it's the next possible mode of vibration after fundamental. I will name this the second overtone because it is the next one that is also possible after the first overtone. Now I can do what I can repeat the same process that I was undergoing under strings. Remember that I said we can express this in terms of wavelengths. Antinode to antinode, I said it before, is half of a wavelength. If I'm going to express this, antinode to a new antinode that I have in the middle is half, and this antinode to the next antinode is also half. So half plus half will give us one wavelength. So here, antinode to the next antinode is half. This antinode to the next is also half, and this antinode to the next one is half. So that will give us 3 all over 2 wavelengths. So if I express this length in terms of the wavelength, I will have L is equal to half wavelength. L here will be equal to wavelength. The L here will be equal to 3 all over 2 wavelengths. I can make the wavelength the subject of the formula, the same process under string. The wavelength here is 2L. The wavelength here is L. The wavelength here is 2L all over 3. Mind you, this is our fundamental mode of vibration. This is our first overtone. This is our second. This is the wavelength of the second overtone. Now that I've been able to get an equation in terms, I've been able to get the equation for the wavelength, I can get the equation for the frequency. Frequency again is velocity all over wavelength. So the fundamental frequency will be obtained from fundamental wavelength. You will discover that F naught will be equal to V all over 2L. Here, the first frequency of the first overtone will be V all over wavelength of the first overtone, and that will be F1 is equal to V all over L. Here, F2 must be equal to V all over lambda 2. If F2 is equal to V all over lambda 2, it means that F2 must be equal to V all over 2L divided by 3. F2 must be equal to 3V all over 2L. If that is the case, I can now, like I did under strings, express each frequency as a multiple of the fundamental frequency. Because we have the same combination that we had under string, I hope you'll be able to see that the first overtone is also 2F naught, and the second overtone will be 3F naught. So the general formula for the frequency here too will be nth overtone must be n plus 1 F naught. Like I said earlier, this number represents the overtone, while the number you are using to multiply the fundamental frequency to get them represents the harmonics. Now, closed pipe. So the combinations that you have for open pipe are just the same with the combination that we had for strings. Now we can continue with closed pipe. For closed pipes are fairly structurally different from the other two, in the sense that we are going to get values that are different from what we have been getting before. I want you to listen and listen attentively. Now, when you check a closed pipe, you see that one end is fixed and the other end is free. If an end is free, I expect it to have an antinode there, and if it is fixed, I expect it to have a node there. The simplest antinode to node combination that we can have in vibration is this. Node represents the fixed end, antinode represents the free end. Then we can continue by adding one more loop to get other forms of vibration of this form. This is an antinode, this is an antinode, and there's a node at the other end. This is an antinode, and there's a node at the other end. So I can find the length here. I can call the length here L. I can call the length here L, and the length here is also L, because it is the same pipe that I'm working with, so they have the same length. One other thing I need to explain to you here is that the velocity too you don't have to calculate the velocity. The velocity does not have to be calculated. If that is the case, we can now get each part in terms of wavelength. The wavelength that node to antinode represents, we derived it the last time, is a quarter wavelength. For this, the wavelength that a node to antinode represents, I'll first take out node to node, which is half, then node to an antinode, which is a quarter. Half plus quarter is 3/4 of a wavelength. Here too, node to node is 1, is half. Node to another node makes it 1, and node to an antinode is a quarter. Half plus a quarter will give us 1/4, which is 5/4 wavelength. Node to node half, another half make it 1, another half makes it 1.5, another half makes it a quarter. That is 1/3 wavelength. So we can continue the same process that we have done for the others. Mind you, since this is the simplest, I will also call it the fundamental mode of vibration. This is going to be our first overtone, and this will be our second overtone. This will be our third overtone. Let me express the length in terms of the wavelength. L in this case will be 1/4 wavelength. L in this case is 3/4 wavelength. L in this case is 5/4 wavelength. L in this case will be 7/4 wavelength. So the wavelength here, I'll make it the solid formula and I'll call it the wavelength of the fundamental. That will be 4L. Here, the wavelength here will be called 4L/3 if I make it the subject of the formula. The wavelength here is the wavelength of the second overtone. It will be 4L/5. The wavelength here will be the wavelength of the third overtone, and it will be 4L/7. If I know that, I can find the frequency. What is F? F is V/λ. That means F must be equal to V all over the lambda is 4L. The F, I expect you to know that is F0. F1 will be equal to V all over lambda 1. F is always equal to V over lambda. The form of your lambda will be the form of the frequency. So F1 will be equal to V all over 4L divided by 3. We can actually take that 3 up. It becomes F1 is equal to 3V all over 4L. F2 in this case must be equal to V all over 4L divided by 5. That means the F2 will be equal to 5V all over 4L. And F3 in this case must be equal to V all over 4L divided by 7. That means F3 must be equal to 7V all over 4L. I can now try to get every other frequency in terms of the fundamental frequency. Remember that the fundamental frequency is V all over 4L. I can have V all over 4L in all of them. F1, this part is V all over 4L. It means if I substitute, I will have 3F0. Mind you, F0 is V over 4L. So if I bring out V over 4L and I put F0, it will give me the ratio of each to the F0. If I bring out V all over 4L here, it becomes F2 is equal to 5 F0. If I bring V all over 4L here, it becomes F3 is equal to 7 F0. If that is the case, we can see the order. The first overtone is the third harmonics is 3 times F0. The second overtone is the fifth harmonics 5 times F0. The third overtone is the seventh harmonic, that's 7 times F0. So we'll see that for a closed pipe, we don't have things like 2 F0. We don't have things like 4 F0. We don't have 6 F0. So generally, it looks like we are not going to be having even harmonics. It is only odd harmonics that are possible on or in a closed pipe. So we can therefore generalize F1 is 3, F2 is 5, F3 is 7. So Fn must be 2n plus 1 f naught. If you multiply 2 by 1, 2 plus 1, 3. 2 by 2 plus 1, 5. 3 times 2 plus 1, 7. It means the next harmonics will be obtained from, the next overtone will be obtained from this formula. And that is how we have been able to prove for the frequency of the closed and open pipe. We now move on to a resonance tube. Resonance tube is a laboratory device that can be used to perform experiments on vibrating air column in a pipe, particularly closed pipe. It simply consists of a tube that has a tap that you can use to run out liquid out of this tube. Of course, there can be a container to collect the liquid. Initially, it is filled with water. Then we have what is called a tuning fork. A tuning fork looks like a normal fork, but it is stronger and the points are longer. And that is because when you hit a tuning fork on the wall, it produces a more elongated sound than your normal fork. If you hit your normal fork on the wall, it produces a very short sound, bang, and that is all. But a tuning fork, because of its longer punch, it produces an elongated sound. It's like bang, such that there is enough time for you to make whatever observation that you need to make. Now, what you do is whenever you have a tuning fork, it comes with its own frequency. It comes with its own natural frequency. So what we are to do is we'll set up the tuning fork into vibration and we'll bring it directly above the tube. We'll bring it directly above the tube. If it is set into vibration and immediately put above the tube while the sound is ongoing, then you open the tap and gradually draw out water. As you draw out water, I want you to know that you are now leaving more space for air. When the amount of air that you have equals to the quantity of air whose natural frequency is going to be equal to that of the tuning fork, there will be resonance. Remember how we define resonance? When an object is set up, when an object is experiencing a vibration at its natural frequency due to an external periodic force that is vibrating also at that frequency, then the object will resonate, the substance will resonate. When you draw out, as you draw out water, there's room for more air. With the quantity of air comes the frequency with which they are going to also vibrate. As the quantity of air changes, the frequency with which they are going to vibrate also changes. A point will come when the amount of air that you have inside the tube is the exact quantity of air that has the same natural frequency as the tuning fork. At that point, how will you know this air will resonate? How will it resonate? There will be a sudden surge in the loudness of sound. There will be a sudden surge in the loudness of sound. If that is the case, let us assume that the water has been drawn out up until this level, such that the quantity of air that we have here is the one that resonated with the tuning fork. We'll take our ruler and we'll measure the length. Let's call it L1. We will repeat the process again. We are going to repeat the process again with the same tube. You are not adding more water. It's still the same quantity of water that is left that you are going to continue with. Because we believe in physics that the tube can actually have different quantity of air that will have the same natural frequency. We believe that if you take out this tuning fork and hit it on the wall, then you return. As you run out water, you will also still get to another point where you will also have a quantity of air that will resonate again with the fork. Let us also assume that that was obtained at this point. Let us pick out our ruler and measure as L2. We can now say that we have the first resonance position and the second resonance position. If we continue, we can have the third resonance position, depending on the length of that tube. What you can easily use as a resonance tube in your laboratory is the burette that you use for your chemistry experiments. You can use your burette easily. And now we have the first resonance position L1, we have the second resonance position L2. What is happening in the first resonance position is that we have a quantity of air that is vibrating with this tuning fork. And the same thing here too, we have a quantity of air that is vibrating in this tuning fork. We believe that when air vibrates, just as I've shown you under open and closed pipe, there is a pattern of a stationary wave that is set up inside it. The pattern of the stationary wave that is set up inside it, I will take the first fundamental pattern. Remember that this represents a closed pipe. The water helps us to move down the fixed end of the pipe. It makes the fixed end of the pipe movable so that we can have different lengths per time. So if we do the same thing here, so this is what I used to represent the first resonance position in the example that we have just seen, and this is what I used to represent the second resonance position in the example that I've just seen. This is the first resonance position that applies to the fundamental mode of vibration, the second resonance position that applies to the first overtone in the example that we have just seen. So I want to express them in terms of wavelength. In terms of wavelength, we said node to antinode must be 1/4 wavelength. Here we said node to node must be half, and node to antinode must also be 1/4. So if you add half to 1/4, you have 3/4 wavelength. If that is the case, then I can say that my L1 must be equal to 1/4 lambda, and my L2 must be equal to 3/4 lambda. It means that my wavelength is equal to 4L. My wavelength here must be equal to 4L2. This is L1, 4L2/3. Resonance tube represents a special case of vibration in a closed pipe, where this time the length is now what is changing, not the wavelength. In the pipe that we have seen, it was the wavelength changing. That was why we had lambda naught, wavelength 1, wavelength 2, wavelength 3, and all of them were determined from a single length value. But here we have the length changing. When the length change, we expect the wavelength to remain constant. So if that is what we need to do, in fact, if I have the first wavelength, from the first resonance tube, from the first resonance position, I can get my wavelength. Once I know the first resonance position, my wavelength will be 4L1. And if I want to find the V, my V is equal to F lambda. Here too, it is only one frequency that we are going to use, and that's the frequency of the tuning fork. Our frequency for resonance tube is not changing. So because there's only one frequency that the system is responding to the frequency. So if I know the frequency of the tuning fork and I know the wavelength, I can just find the velocity as F multiplied by 4L1. And that becomes the velocity, which is equal to 4FL1, if L1 is the first resonance position. So resonance tube can also be used to find the velocity of sound in air. But this is a simplified form. There are times when this fork will be slightly displaced above the surface of the tube. In that case, our wave, the antinode of our wave, will start from the point where the fork is. The antinode of our wave will start from the point where the fork is. And that is where we are going to measure 3/4 lambda. That is where we are also going to measure 1/4 lambda. But the L will be measured from the top of the tube. We will now clearly see that our L1 is not exactly equal to 1 all over 4 lambda. Our L2 is not exactly equal to 3 all over 4 lambda. So we can call this extra length that has been added the end correction. The end correction. So end correction is brought into the equation because of the fact that you are slightly displaced your tuning fork a little above the level of the tube. And why is that necessary? Your fork must not come in contact to your tube. If it comes in contact to your tube, both your tube and the air inside it will start to vibrate, and what you are going to be responding to is actually complex vibrations that will be very difficult to monitor. So it is one of the precautions is that the fork must not touch the tube, but it must be as close as possible to the tube to ensure that the end correction is not significant. Where the end correction becomes significant, then we can rewrite our equation as it is now L1 plus the end correction that will be equal to 1 over 4 lambda. 1 over 4 lambda will be L1 plus the end correction. And also 3 all over 4 lambda will be L2 plus the end correction. If we subtract, by solving them simultaneously, 3 all over 4 minus 1 all over 4 will give you half lambda, L2 minus L1, and E cancel out E. So if we equal to 2 L2 minus L1, that means that V is equal to F lambda. If V is equal to F lambda, it means that V must be equal to F multiplied by lambda 2L2 minus L1, and that should be V is equal to 2F open bracket L2 minus L1. And that is the formula that we are going to use to find the velocity if there is end correction. We can also use this formula if there is no end correction, but this is more appropriately used if there is end correction. And even with this formula, we can now get more resonance position. If V is equal to 2F L2 minus L1, I can also say that V is equal to 2F L3 minus L2. V will be equal to 2F L4 minus L3. Just find the difference between any two consecutive positions, multiply by a frequency, multiply it by 2, that will give you the velocity. But in this case, where there is no end correction, the only thing you just need to know is to know the next form of wavelength that you can. For example, if my L1 is 1 all over 4 wavelength, my second resonance position L2 will be 3 all over 4 wavelength. My third resonance position will be in that same order. That will be 5 all over 4 wavelength. And my next resonance position will be 7 all over 4 wavelength. So with that, we have come to the end of the calculation. Like I was saying earlier, the next thing is how many is the number of musical instruments that we have. And we have 3 musical instruments. One is percussion. If an object has to be beaten, hit, or struck on the instrument before it can produce sound, it is a percussion instrument. Drum is a very good example. If the instrument has a vibrating air column within it, then it is a wind instrument. Flute is a very good example of wind instrument. And if the instrument has a string, a vibrating string on it, then it is an example of a stringed musical instrument. A very good example under that is a guitar. So we'll now take examples. The first one, a sound pulse projected vertically downward into the earth is reflected from 2 different layers of the earth, such that the echoes are received after 1.5 seconds and 1.8 seconds. If the speed of the pulse is 2,000 meters per second, what is the distance between the layers? We have 2 different layers in the earth. Sound pulse was projected down, and it was reflected at different times. One was sent back after 1.5 seconds. The other was sent back after 1.8 seconds. we are asked to find the difference between the two layers of the earth. Let us call the distance here x, and let us call the distance here y. So the first pulse that was returned must have traveled a distance that is equal to 2x. It came down by x, and it was reflected, and it went up by x. The second pulse must have traveled a distance that is equal to y plus y, that is 2y. So the time spent here is 1.5 seconds. The time spent here is 1.8 seconds. We are given the velocity of the pulse in both cases. This 2,000 meters per second. Here the velocity is also 2,000 meters per second. If that is the case, I can now find x here and y here. I hope you know that what I want to get now must be the difference between x and y. Our velocity is equal to distance over time. That means velocity 2,000 must be equal to distance 2x all over time 1.5. 2x is equal to 2,000 multiplied by 1.5. X must be equal to 3,000 divided by 2,000 times 1.5 is 3,000 divided by 2. That is 1,500. That is 1,500. For the other, we have velocity 2,000 is equal to the distance. The distance is 2y divided by 1.8. That means 2y must be equal to 1.8 times 2,000 is 3,600. If we divide that by 2, we have 1,800 meters. So the distance between the two will be y minus x, and that is 1,800 minus 1,500. The answer should be equal to 300 meters, and that's the distance between them. The second question. Here we are told that a string of length 50 centimeters and mass 10 raised to the power minus 3. The length of that string is 50 centimeters. I would like to convert it to meters by dividing by 100. That should be 0.5 meters. And mass 10 raised to the power minus 3. The mass is equal to 10 raised to the power minus 3 kilogram. Vibrates in 5 loops. It vibrates in 5 loops. I can represent the 5 loops as 1, 2, 3, 4, 5. In stationary form, 1, 2, 3, 4, 5. This is loop 1, loop 2, loop 3, loop 4, loop 5. How many overtones do you think this will represent in a string? Sometimes they will give it to you in overtones, sometimes they will give it to you in loops. You can count. For string, these are first fundamental. Revert back to what we did while we're explaining vibrations in string. This is the first fundamental, represent the first overtone, the second overtone, the third overtone, the fourth overtone. Fundamental, first overtone, second, third, fourth. So they are talking about the frequency of the fourth overtone. If they want us to find frequency, they are talking about the wavelength of the fourth overtone if they want us to find wavelength. But we can continue. They said it vibrates in 5 loops. We asked if the tension in the string is 20 Newton, what is the frequency of vibration? If the tension in the string is 20 Newton, what is the frequency of vibration? The very first thing we should do is to find the mass per unit length. Mass per unit length, I told you, is the mass all over the length. The mass is 10 raised to the power minus 3. The length itself is 0.5. If you do that, you will have 2 times 10 raised to the power minus 3. If that is the case, I can now find the velocity. The velocity is t all over m, and that will be square root of our t is 20. We'll divide it by 2 times 10 raised to the power minus 3. That should be 10. 20 divided by 2 is 10 times 10 raised to the power 3. and that should be 10 raised to power 4. So our velocity will be square root of 10 raised to power 4, which is 100 meters per second. If that is our velocity, then we can find our F naught. Always know the formula for your F naught. F naught that's the frequency of the fundamental vibration. F naught for a string, we got it to be V all over 2L. That will be V, 100, divided by 2L, 2 times the length, and the length is 0.5. So F naught must be equal to 100 divided by 1. If I know F naught, then I can now find F4. Remember that there's a general formula that we give for finding other frequencies from F naught. That is n plus 1 F naught. If that is the case, that will be F4 will be 5 F naught. That will be 5 multiplied by 100. 5 multiplied by 100 is 500 hertz. And that is the end of the question. We can still continue with more questions. In the third question, we are asked to determine the pitch or the frequency of the fundamental and also the first two overtone. The pitch of the fundamental F naught and the first two overtone F1 and F2 of a closed pipe, B, an open pipe if each pipe is 67 centimeters long. The closed pipe is 67 centimeters long. If it were to be an open pipe, I'm also to assume that it is also 67 centimeters long. And the temperature is 20 degrees Celsius. We are to do it at a temperature of 20 degrees Celsius. We take the speed of sound at 20 degrees Celsius to be 343. The speed of sound at the temperature that we want to use is 343 meters per second. The speed of sound is 343 meters per second. Why did they give us the temperature with the velocity? Because I told you earlier that temperature can affect velocity, but they want us to do this at 20 degrees Celsius and they give us the velocity at 20 degrees Celsius. If the reason why they give us the velocity with the temperature is because they know that the velocity can be affected by temperature. But we don't have any problem with that in this question. They asked us to find F0, F1, and F2 at 20 degrees Celsius, and the velocity they give us is also at 20 degrees Celsius. In a situation where the velocity they give us is at another temperature, and they want us to solve this question for 20 degrees Celsius, then we must use the formula that I derived earlier, V1 all over square root of theta 1 in Kelvin must be equal to V2 all over square root of theta 2 in Kelvin to get the velocity that you will use at 20 when the velocity has been given in another temperature. But that is not our problem for now. So we can now just go straight into the question. I want us to look at it. We are given the length. We can convert it to meters. That will be 0.67 by dividing by 100. So if I know the length, I want to find F naught. F naught for a closed pipe is V all over 4L. You must know the formula for finding F naught for string, for closed pipe, for open pipe. Either you just know it or you know how to derive it. Because F naught is central to every other frequency. If I know F naught, then I'll be able to use the general formula of that particular instrument to determine every other frequency. The V is 343. The L is 0.67. And I will get that as 343 divided by 4 times 0.67. That's 127.99, which is approximately 128 hertz. Remember that the general formula for finding other frequencies for closed pipe is 2n plus 1 F naught. So F 2 F1 that they want me to find. If I put 1 here, 2 times 1, 3 plus 1 is 3 F0. That will be 3 times 128. That is why F0 is good. If you know F0, you can get every other one. F2 will be 2 times 2 plus 1. That will be 5 F0. That will be 5 multiplied by 128. If we do that, we have our answer. 384 Hertz. Y 5 times 128 is 640 Hertz. And that is all about that. I will do the same thing for the open pipe. Sorry, this is the open pipe. This is the closed pipe. Now, F0 for the open pipe is V all over 2L. That means V 343 divided by 2 times L. 2 times L is 0.67. If you do that, you are going to have 128 times 2. This will give you 256 at F1 will now be, because the general formula for all frequency in an open pipe, we derive it earlier, is N plus 1 F0. That will be V. That will be F1 will be 2 F0. That's 2 times 256. And 2 times 256 should give us 512 Hertz. While F2 must be equal to 3 times F0. And that will be 3 times 256. 3 times 256 should give us 768 Hertz. And with that, we have come to the end of this question. We'll now look for one more question on resonance tube. The length of the vibrating air column of a simple resonance tube can be altered by adjusting a water level. Resonance is found for a fork of frequency 440 Hertz. When you are solving a question on resonance tube, they will give you only one frequency and you have only one wavelength. It is the length that will be changing. It's not like an open, closed, and string, open, closed pipe and string, where the length are constant and the frequency and wavelength are changing according to the fundamental or the overtone that we are dealing with. Here, we are now told that resonance is found for a fork of frequency 440 Hertz when the length of the air column is 18.87 and again when it is 57.3. When the length is 18.8 centimeters and when the length is also 57.3 centimeters, 57.3 centimeters. I'll call this the first resonance position. I'll call this the second resonance position. We are asked to calculate the speed of sound in the air, in the tube, and the position of the next resonance as more water is run out. We want to find the position. We want to find the velocity. Remember that the velocity of sound in a resonance tube can be obtained from L2 minus L1. The velocity will be 2 times 440 multiplied by our L2 is 57.3. I can change that to meters. That will be 0.573 minus our L1 is 0.188. With the multiplication of the necessary quantities here, we should have the answer. Our answer is 338.8 meters per second. That is it. We are also asked to now find the position of the next resonance. Remember that I said that V can also be obtained by subtracting the next two consecutive resonance positions. V I now know to be 338.8, which is equal to 2 times F. Our F is 440. Open bracket, L3 is what I don't know, but I know my L2 to be 0.573. So I can solve for L3 minus 0.573 must be equal to 338 divided by I have 0.385. That means that my L3 must be equal to, if I take this to the other side, 0.385 plus 0.573. 0.385 plus 0.573 should give me 0.958. 0.958, or better put, 95.8 centimeters. And with that, we have come to the end of this very interesting topic. I want you to join us the next time as we continue to dissect the topics that we have in the physics curriculum. Thank you very much.